We will now learn about Rolle's theorem. So Rolle's theorem states that let f be a function that satisfies the following three hypotheses. Number 1, f is continuous on the closed interval a to b. Number 2, f is differentiable on the open interval a to b. Number 3, f of a equals to f of b. Then there is a number c in open interval a to b such that the derivative of f evaluated as c, so f prime of c, is equal to 0. So let's start with this graph right here, and let's look back at the conditions. So we have an interval, the closed interval a till b. We can see that the graph is continuous, and we can also see that it's differentiable at every point, because we stated earlier in earlier chapters that it either has to be discontinuous, or we need a sharp corner, or a curvy corner, or we need a vertical tangent line for it to be not differentiable. However, we don't see any of that in here, so it's differentiable on the open interval. And regarding whenever we say that it's differentiable, we always use open intervals. And we have that f of a here is equal to f of b. Therefore, there is a point in between a and b, and we can see here that c is here. There is a point such as the derivative is 0. Whenever the derivative is 0, we can see that the tangent line is horizontal, which is the case for the point c here. Now let's look at this graph. This graph is here to show us that we can have more than one point. But the Rolle's theorem guarantees that there is a number c. There can be more than one, there can be three, but the theorem guarantees that there is at least one. And now let's look at the other example. Again, we see that this is our horizontal tangent line and this is our point C. Now let's go back to our first example. This example is just here to illustrate that even if we have the entire function is a horizontal line, even if it does not vary, then we do have points C at every point in between A and B. And here this graph illustrates two of them, so C1 and C2, where if we were to draw the tangent line, it is a horizontal tangent line, and therefore since the tangent line is horizontal, then the derivative evaluated at these points is 0. So let's move on to an example to see how this can be applied. So we will now apply Rolle's theorem on the function f of x equals to x sine x on the interval 0 to pi. So let's look at the conditions. Condition 1 is that f has to be continuous on the closed interval a to b. So we have to state that f of x is continuous on all the real numbers, so it is continuous on the closed interval from 0 to pi. Just to note that x itself is continuous on all the real numbers, and sine of x is also continuous on all the real numbers. Now let's look at the second condition. F has to be differentiable on the open interval a till b. So, let's differentiate x, and this will become clear to us. So f prime of x, this is the product rule. We keep the first term, we multiply it by the derivative of the second term. Then we take the derivative of the first term, we multiply it by the second term. So this is x cos x plus sine of x. And we can see that it is so f of x is in fact differentiable on the open interval 0 up to pi. Now our third condition is f of a has to be equal to f of b. Please note that 0 is our a and pi is our b. So f of 0 is equal to 0 sine 0, which is equal to 0. F of pi equals to pi, sine of pi. Sine of pi is 0, so this entire thing is 0. And we can see that f of 0 equals to f of pi, so we have satisfied the third condition as well. Now we can say that Rolle's theorem applies. Thus, there exists C belongs to the open interval 0, 2, the open interval 0 pi, such that the derivative of f evaluated at C is equal to 0. So this means, where did we already evaluate the derivative of f? It is right here. This means that C cosine of C plus sine of C is equal to 0. And this is how we apply Rolle's theorem. Let us now move to a slightly more complicated problem that involves Rolle's theorem. We want to prove that the equation x cubed plus x minus 1 equals to 0 has exactly one real solution. Such types of problems, we do them using IVT and using Rolle's theorem. So we start by IVT to show that this equation has at least one solution, and then when we finish that, we use Rolle's theorem to show by contradiction that it cannot have more than one solution. So let us begin with IVT. So, first of all, our function, let f of x be x cubed plus x minus 1. We will choose an interval such that the first point gives us a negative answer, but the upper bound of the interval gives us a positive answer. So we will choose the interval 0, 1. You can just choose this interval by trying several points, literally by trial and error. So f of 0 is equal to 0 cubed plus 0 minus 1, which is equal to negative 1, and this is less than 0. F of 1 is equal to 1 cubed plus 1 minus 1, which is equal to 1, and this is greater than 0. Now, this is one of the conditions for IVT. Also, please note that the function has to be continuous on this closed interval. So f of x is a polynomial. Therefore, it is continuous on all real numbers. Therefore, it is continuous on the closed interval 0 to 1. Now, let's continue. So the IVT states that there exists a number C between 0 and 1 such that f of C equals to 0. Therefore, the given equation has a solution. Now we have proved that it has a solution with IVT. We need to prove with Rolle's theorem that it cannot have more than one real solution. So let's move on to Rolle's theorem. So we will argue by contradiction. What this means is that we will suppose that the equation has two solutions, and then we will show that this cannot happen. So suppose that it has two solutions, A and B. So f of A equals to f of B equals to 0. And now we will show that we will say that it is continuous and differentiable for us to be able to apply Rolle's theorem. Since f is a polynomial, then it is continuous on the closed interval AB and differentiable on the open interval A till B. Because of that, we can now apply Rolle's theorem. Thus, by Rolle's theorem, there exists a number C between A and B such that the derivative of C is equal to 0. Now, what is the derivative of f of x? The derivative of f of x, so f prime of x, our function is x cubed plus x minus 1, so the derivative is 3x squared plus 1. Now, something you might notice about that is that 3x squared plus 1 is always greater than or equal to 1 because the smallest value we can get for 3x squared is 0. Because even if x is negative, let's say x is -1, -1 all squared is 1. We multiply this by 3, then we get a 3. So the smallest number we will get for 3x squared is 0, and 0 plus 1 is 1. So 3x squared plus 1 is greater than or equal to 1 for all x. I will write here, this is because x squared is always greater than or equal to 0. However, we have just stated before that the derivative of the derivative of f evaluated at c is equal to 0. And we just said right now that the derivative is greater than or equal to 1. So we should write that this cannot happen. This is a contradiction because f of x can never be 0. So this gives a contradiction. Therefore, the equation cannot have two real solutions. And now we have proved, so thus the equation has only one unique real solution. So we have proved using IVT and Rolle's theorem that the equation has exactly one real solution. We will now move and learn about the mean value theorem. So what is the mean value theorem? Let f be a function that satisfies the following hypotheses. Number 1, f is continuous on the closed interval a to b. Number 2, f is differentiable on the open interval a till b. Then there is a number c in ab such that the derivative of c equals to fb minus fa divided by b minus a, and we can rewrite this as f of b minus f of a. We can just move the b minus a to the other side, so this becomes f prime of c times b minus a. So let's see what this means on a graph, because maybe the wording is not really clear. So first of all, let's check if we satisfy all of the conditions. Let's check the first graph. So f is continuous on the closed interval a till b, which we can see is the case here. The graph of f is in black. And then f is differentiable on the open interval a to b, which we can also see is the case for us, because as we said earlier, for f to be not differentiable, we either need a sharp corner or a curvy corner, which we also call a cusp, or we need a vertical tangent line, or we need a discontinuity, which we don't have any of these here, so f is differentiable on the open interval a to b. Then there exists a number c in a till b, in the open interval a till b, such as the derivative at point c. So now we drew this tangent line, the slope of this tangent line, which is the derivative at point c, it is equal to f of b minus f of a divided by b minus a. Basically what this is saying is that the slope of the tangent line at point C, it is equal to the slope of the line connecting the points A and B. Let's look at another graph. We have point A here, point B, and then we have the graph of f of x in black. And we can see that we have more than one point C. So here we have a point C, and this is its tangent line. And we can see that the slope of this tangent line is the same as the slope of the line connecting points A and B. And then we also have another point C2 here, which has a slope which is also the same slope as the slope of the line connecting A and B. So in this case, we have more than one point C. And now we will apply this with an example. So we will apply the mean value theorem on the function f of x equals to x cubed minus x, and we will use a equals to 0 and b equals to 2. So how do we apply the mean value theorem? So let's go back to the conditions. The first condition is that f is continuous on the closed interval a till b. So let's start by saying f is a polynomial. So it is continuous on all real numbers and therefore continuous on the closed interval a to b, so 0 to 2. This is condition 1. We got it. Now let's move on to condition 2. F is differentiable on the open interval ab. So again, since f is a polynomial, therefore it is continuous. And again, we can write this f is a polynomial. So it is differentiable on the open interval a till b. So we got the second condition. Just to point out, if you're ever not sure where f is differentiable, you can always find the derivative. So the derivative of f is 3x squared minus 1, which shows that it is differentiable on all x and therefore differentiable on the open interval 0 to 2. Therefore, we can apply MVT. So MVT applies, and there exists, we can conclude that there exists C in the open interval 0 to 2 such that, again, let's go back and look here. So let's use this form down here, which is simpler. F of b minus f of a is equal to f prime of c times b minus a. So f of 2, because b is 2, minus f of a, so f of 0, is equal to f prime of c times 2 minus 0. Let's write this down. F of 2 minus f of 0 is equal to f prime of c times 2 minus 0. What is f of 2? So the function is x cubed minus x. So f of 2 is 2 cubed minus 2, which gives 6. F of 0 is 0 cubed minus 0, which is 0. And we already found f prime of x to be 3x squared minus 1. So let's replace. 6 minus 0 is equal to f prime of c. So if f prime of x is 3x squared minus 1, then f prime of c is 3c squared minus 1. And we multiply this by 2 minus 0. So we can write this as 6 equals to 3c squared minus 1 times 2. And now, so 6 equals 2. Let us now multiply both terms by 2. So we get 6t squared minus 2. And then let's try to solve for c squared. So 6c squared is equal to 6 plus 2, which is 8. Then c squared is equal to 8 over 6. We divide both the numerator and the denominator by 2. And this gives us 4 divided by 3. Let's solve for c. It's equal to plus minus square root of 4 divided by 3, which is equal to plus minus 2 divided by square root of 3. And let's go back and look to the interval that c belongs to. We said earlier that c is in open interval 0 till 2. So the first value of positive 2 divided by square root of 3 does belong to this interval. However, negative 2 divided by square root of 3 does not belong to this interval. So let us write this down. C belongs to the interval 0 till 2. Therefore, C is equal to 2 divided by square root of 3. And this is how we apply the mean value theorem to a function.